Dear all, I guess it's time to start the next session, and I'm happy to introduce the next invited talk given by Leonard Kwuida. Uh, Leonard holds a PhD from Technische University Dresden in algebra and logic, and his research interest includes formal concept analysis, data analysis, algebraic operators for knowledge discovery, explainable artificial intelligence, ordered structures, weak types of negation, and others. So now he teaches at Bern University of Applied Science, and I'm very interested in what is going to happen in the next talk. So Leonardo, please.
Thank you for the kind introductions, and thank you also for giving me the opportunity to share this work with you. So I'm going to start by sharing my screen. And if you don't see them, please let me know. So can you see my screen?
Yeah, the slides, we can see them.
Oh, okay, I think that's enough. Yeah. Okay, so then what I'm going to discuss with you is some idea about the interpretability in concept-based machine learning. So it's also a nice thing that my talk just happened to be after that of Miguel, because he has introduced most of the concept that we also need here. And the talk will be, they say the first part will be on the interpretability of the concept-based machine learning. And in the second part, then we are also going to stress in the interpretability, but this time looking at the stability of concept. So the third part, I will let you know later, so to keep you awake. Okay, so then let us start. So we have here two pictures, and the question is, which one should you adopt? The question is for you. Okay, it doesn't matter which ones you, maybe you have make your decision already, but the question is, how do you come to your decisions? So is it possible for you to explain your choice, or if you let the program do it for you, is it possible to explain the choice that's of the program? So then we have one thing here. This means we have to first to understand what these images are telling us, then extract some information from this and use these information to classify these two photos. So this is what we will expect machine learning to do. But the main question is, after classifying, is it possible to explain why we come to a certain classifications? Okay, so then our goal is, for example, to try to give an interpretations of what leads to a special classifications. That's what we are going to discuss in the first part, which is this one. So the method that we are going to use is the ones that Sergey has discussed many times in the setting of formal concept analysis. That's the JSM method. And there are also some other methods for the let's say, for this classification, but we are not going to discuss this, the version space. We are not going to discuss that in this case, but there are many other methods. So for the interpretation, the interpretability, so what we are trying to do is once you have make a classifications, then this classification is based on the attributes that you have in your model. The question is whether all the attributes play the same role, or are some attributes more important than the other in this process of the classifications. To discuss that, then maybe we should have a close look at what the JSM method is doing exactly. So the JSM method is named after John Stuart Mill, and it's an idea to let's say to go from the try to transform the inductive reasoning into deductive reasoning. So the idea behind is that if two or more instances of the phenomenon on the investigations share exactly one's common circumstance, then we believe that this actually is the cause of this phenomenon. So then we are going to try to solve, if you generate the rules and then you want to classify something, then you are going to look what are the common thing between what is not yet classified and what are already known to be classified. Okay, this is a bit how the idea behind the JSM methods, and this has been formalized in the FCA setting. And what we are going to discuss, because we are, let's say, from the FCA side, then to look a bit at the setting in the FCA. And we have said that, so we want to look at the setting of the JSM method in the FCA. And in the FCA, the basic, let's say the basic notions of the FCA is the notion of concept. And what is a concept? If the traditional philosopher, they look at it as something having an extent and an intent. So the intent will be all the attributes that describe the concept, and then the extent will be the object that belong to this concept. In the FCA setting, we look at the JSM method as a kind of rule where you have the concept intents imply a class. So the concept intents, that's a set of attributes. So then we say that if an object satisfies this set of attributes, we will assign to this object this class. So maybe we will just give you a definition again of what we mean by implication, or what we mean by a rule. So then also in this case, so we have the concept intent, which is a set of attributes. We can look at it as a coalition. And the question is whether all these attributes are playing the same role, or if some are more important than the others. Then to assess the importance of the attributes, then we will borrow some notion from the game theory. And in these presentations, we are going to stress on the Shapley value. This is let's say a function that will help us, for example, to compute the importance of each individual in the coalitions, so that if we were to redistribute the gains, then we will do it in a fair way. So some notion from the FCA, that the setting, what we have is the starting point is a binary relations where you have a set G of object, and then M of attributes, and the binary relation E is just to tell you if an object has an attributes or not. To get the notion of intent and extent, then if you start with a set of objects, then you can look at all the attributes common to all these objects. This will be the A prime. And if you start with the set of attributes B, then you can look at all the objects that have all the attributes in B. So then you have these two derivation operator, and a concept is nothing else like than a pair AB, where A prime is B and B prime is A. And in this case, B is the intent and A is the extent. So then we are going to, for the case of the rule, we are going to concentrate on the intent. So that's just recalling what an implication is. Intuitively, we think that if H, which will be hypothesis here, imply M, so this means M will be the representing the class. So if we have something like this, then we believe that each object that has all the attributes in H should also have the attributes M. Okay, so now that we have defined the notion of intent, then we look at the GSM setting in the FCA. So what is the setting? So we start with a context, and there is a target attribute which is not in the context that we are working with, and this attribute will separate the set of objects in three groups. Then we will have the positive example. That are those objects that we know that they satisfy that they belong to the class. And then we have the negative example. These are also those that we know that they do not have the attribute V. These two parts, the positive and the negative, we will use that to form to get our training context. So this will be, we'll train the model on this, and the goal will be to use the train model to classify the object that are not yet the object that we don't know the type now. So for the notations, we just rewrite the three subcontexts that we have discussed before. So you have the positive, the negative, and the unknown part, and the training context, which is putting together the positive and the negative example and having these relations. So the goal is to classify the object that's the object that we don't know the type now. This will be for the third context. If we pull all the three contexts together, then so we get what is called the classifications context. Okay, so this is the setting, but now we have to discuss how do we classify an object to belong to a class or not. So what are the rules? To do that, then we are going to generate the hypothesis, and we will call a subset H of attributes a positive hypothesis if it's an intent of the positive context, and this will be an intent of the positive context, and this intent should not contain the intent of any negative example. So this means we want to believe that all the objects there will have the will belong to the class, and so we don't want to have a counter example that will have an object which is satisfying all these attributes but is belonging to the class of object not satisfying V. So then in that case, we also have, in a similar way, the negative hypothesis. This will be the intent of the negative concept, but that do not contain the intent of any positive example. So once we have the hypothesis, positive and negative, then we can now use that to make our classifications. And so here we have an example of a context which is about classifying people who are according to the, let's say, the credit score, if they can get a credit or not. And we have the attributes here. If the first thing that you notice is that the attributes are not binary, but then we can transform it to get a binary attributes. So then we will add a new line, which is a new column where we have MA and F and so on. Then we just discretize the attribute here. And using the new context, which is a binary, then we can construct the, let's say, the line diagram of our positive and negative context, and then we can see what will be our positive hypothesis and negative hypothesis. So on the line diagram that you have on the left, for example, that will be that of the positive context. Then we can look at the nodes A that we have here, and these nodes, the intent of this node is actually the upper, let's say we look at the upper parts, then we have the attribute A, F, M, E, and H, E. So this will be the intent that we have. And this will be a positive hypothesis in our case. And in this context here, we have exactly two positive hypotheses. This will be the ones with the node A and the other one with the node SS. In a similar way, we can compute the negative hypothesis. There will be the red node on the second line diagram. So the rules, we say that we will classify an object positively if the intent of this object contain a positive hypothesis and no negative hypothesis. So this means if we look at all the attributes satisfied by an object G, and if it contains a positive hypothesis and there is no contradiction, then we will assign it to the class. And the second case, if we look at all the attributes satisfied by the object G, and if this contains a negative hypothesis and there is no contradictions, then we will assign its, will classify it negatively. There is a third case where we say, okay, we are not able to make the classifications. For example, if you have, if the G prime contain both positive and negative hypothesis, then you have something which is contradictory. Or if it contains none of them, then we still have something which is undetermined. So we have the rules, and we can apply this on this our example of credit scoring. We have two positive hypotheses and three negative hypotheses, and we take, for example, the G9, G9. If we look at the object G9, and look at all the attributes satisfied by this object. Then we notice that it contains the positive hypothesis high, that's high HS, which is high salary, and no negative hypothesis. Then in that case, we will classify it positively. This means he will get the credit. So, and the next object, which is tens, and then we can look at the common attributes. It does not contain neither positive nor negative hypothesis. Then in that case, we think that we are not able to classify, or this means this needs further considerations. We cannot just classify it with our training data that we had. In the same idea, then we can look at the rest, the G11s and 12, and then we make the decisions. So the attribute that we use to make this classification here are those in the intent of the object. And the question is whether some of the attributes were more important than the other. So that's what we should discuss. And to discuss that, we are now looking at the idea of the interpretable of the classification that we have done. Let us assume, for example, here you have a model that will predict the range for the flat, and you train a model, and then you get let's say that the average range will be like the average price will be like 300,000. So to the range, you assume that you have a model, and say if you train this model to predict the price of the apartments, then you get like 300,000, and you want to check what is the importance of the attribute according to the description that you have. Then maybe you have that there is a park nearby, or the apartment is in the first or second floor, and so on, or you are allowed to have an animal or not. The idea is that you try to look at what happens to the predictions if you remove one's attribute. So, for example, if you remove the cat, or if you add the cat, then you can now use that to see what is the influence of this single attribute. And you can do that because you have a coalition, and then you can all try to check what will be the prediction if I use this attribute or if I don't use this attribute. So that's the idea that we want to use, and we are going to borrow the idea from the game theory. That is the Shapley value. And what is this actually? He tried to compute the expected. So he tried to use the expected value of the model predictions, considering so you have a subset S. This is like a coalitions, and then you concentrate on an attribute M, and then you try to see what's happened if M is in the coalition or if M is not in the coalition. Then you try to look at the difference in the expected predictions and take the average on all the subset of the coalitions. So the f of x with S with the S union M, that will be the coalition where M is part of it. And here we assume that S is not S is subsets of M that do not contain the attribute M. So if we compute that, we should look at the value, and the value give of a certain indications on the importance of each of the attributes. So to compute that, we need to define our fx. And in this case, because we want to classify our object, then we will take as the fx, which is here called the v. This, we want v to have the value once if we classify. So if this helps us to classify it positively, and -1 if this is to classify negatively, and 0 if we are not able to classify. So then this v is our indication function that we have from the fx that we are using here. So okay, so we have our function, which is Vm of g, and the next thing is to compute this once we have done a classification. So how does it work? At least for the example that we had before, we can just do the computation as it is. Let's say just a naive way without thinking of how say optimal computation or not. We just compute the vector of each of the 4 attributes that we were trying to classify. So in the case of the object 9, we classify it positively, and it was containing only HS, the highest salary as positive hypothesis. And in this case, if we compute the Shapley vector, then we see that only the attributes 9 has non-zero value, which is exactly 1. If we do that for the 10s that we're not able to classify, then we get actually 0 here everywhere. And for 11s that we classify negatively, so we here also gets negative value almost everywhere. And at least here you see that the -2/3 is the, let's say, the largest in absolute value, meaning that this attribute there seem to be more playing an important role than the others. So then we can do that for all these. We have done these experiments, and what we notice is that if you compute the sum of all the Vm, so you fix the G, you will take all the attributes satisfied by G, then you compute the sum of this. This means that you add everything what is in the vector. Then you will get 1 if G is classified positively, -1 if it's classified negatively, and 0 if you cannot classify the object. So we have done this experiment also on the Zo data sets, and then we have some similar behavior. So the description of the Zo data sets, you can maybe read it later. So we have a data set where most of the attributes are Boolean, except one which is numeric, but we convert it into, let's say, we just use the nominal scale and transform it. So we compute the positive and the negative hypothesis. In this case, we have only one, and we want to classify the object, let's say the animal, want to classify the dog. So what we see here, the classification, the target attribute here is mammal. So then we want to classify, see if we say we classify positively, this means that we believe that this is a mammal, and if we classify negatively, then we believe it's not. And it's possible that we also give up and say we are not able to classify. So in the case of the dog, then we look at all the attributes common to it, and the question is whether some of the attributes here are more important than the other. Then in that case, we complete the Shapley vector of this object. And we can represent it here in this lollipop diagram. And then what you notice is that 3 attributes are here, actually the ones who are playing a great role in these classifications. And these are the eggs, breads, and air bones. So although we have many attributes in this in the satisfied by the dog, so for classifying it as the non-mammal, we think that these 3 attributes are the one playing the important role. So then that's the first part, that we have an idea a bit what's how we can use the Shapley value to interpret the result of a classification. The second part is similar. We are still going to use the Shapley value, but this time is to look at the stability of the concept. So the stability was introduced by Sergey, and then the idea was that if we look at the intent of a concept, and maybe we remove some of the attributes, do we still generate with the rest of the attributes the concept that we have? So then we try to see the robustness of the concept. This could be on the object elections or attributes and so on. So then also in that case, we try to see if looking at the stability of a concept, some attribute will play a role which is more important than the other. The idea is actually the same. What we need is just to, so if we go back a bit, look at how the Shapley value was defined. So here, then what we need here is to define our new function fx. So how do we
I'm sorry, I cannot hear your voice. Leonard, are you here?
it stopped, it freeze from 20 something?
24.
24. Okay, so in the slide 24, it's was introducing the importance of attribute for the stability of the concept. And then we have defined the notion of stability as the proportions of subset generating the intents according to the number of, with respect to number of candidates. And then we said that what we need into input in the Shapley formula is to know what is our function fx, and in this case we take v to be 1 if y is a generator of p, and 0 if not. So then we input it there and we can compute our vector. So there are, let's say from the computational point of view, there are some simplifications that can be done to get these computations. I will skip the simplifications. If you want to check it, then it is in one of our paper that we can provide, or that you can find it from the CLA. But we look at one example how this works. So we take a part of this context with the fruit context, and we are going to compute its concept like this, and then the stability of the concept, and try to look at the importance of the attribute. So what we consider here is just the positive part of this context, and compute the stability of this context. This is what you have in the second column, and then also computes the Shapley value for each of this concept. What you can see, for example, in the first case is that the attribute S, which is in the first concept, is having importance 0. And in almost all these cases, so then if you go back and look at this attribute, so we have this S, and he's in the concept that we got, he's actually not playing a role. So then computing this vector, we will be able to, let's say, to access the importance of each of the attributes that we have in our intent. Okay, so this experiment has also been done on the Zo data set, and we can get what can we say? We can try to represent the with these diagrams the Shapley value of all the attributes that are in an intent, and then to see which one are more important than the other. So if you here we look at the first 3 most stable concepts. So the first one, which is G empty sets, so there is no need to show the vector because everywhere you have just 0. And the second, he classify all these attributes according to their importance, and then the question is probably, yeah, is it possible maybe to use that to remove some of the attributes, or if we want to reduce the number of attributes, maybe we can try to look at the importance of the attributes computed using the Shapley value, and then we can remove some of these. This is one thing. This means that we probably use the attribute in importance and make a kind of ranking. Here, notice that our ranking box is always a kind of local, but maybe we can think about something which will be like generalizing, so averaging, so that we have a ranking on the total, on the whole context. And in that case, we might find out that some of the attribute that we have is not quite important, and maybe we can't remove these attributes when we are working with too many attributes. So another option of reducing the number of attributes is to look at the similarity. And here the idea is that if two attributes, if we believe that two attributes are similar, then we can put these attributes together, and instead of having two columns in our data set, then we just have one column. But when you put two attributes together, then you have to decide how to assign the object to this attribute. This is what we're going to discuss a bit here. So in some cases, then you have, let's say, an ontology, or you have a taxonomy, and this taxonomy tells you that an object, you can have this taxonomy on object or on attributes, or things, but for example, that something belongs to another class and so on. And using that, then maybe we can stop somewhere, and instead of working with the large set of attributes, we reduce and take just part of it. The idea, if according to my present knowledge, the idea came first in the paper by Agravan, where they were trying to get generalized association rules. And what do they understand by generalized association rules? So if you look at this example, this is a database for transactions, and on the right you have a taxonomy. And if you concentrate and you want to find the rule only on the database on the left without using the taxonomy, then you probably miss some important rules. But if you take into account the taxonomy, then you can discover some of the rules that you were not able to find before. For example, that's outwear will imply hiking boots, or that how highwear, outerwear imply footwear. So that you can have this kind of rule that you were not able to see in the first, if you just work with the initial data set. But what you have here is that you try to discover some rule combines with, let's say, the general classes introduced by the taxonomy. But the problem that we wanted to solve was, if we have too many attributes, is it possible to reduce the number of attributes or not? That's actually the problem that we have. But here, in this case, it seems like we have increased the number of attributes by adding also those where we have the those from the taxonomy. Just some notation and definition what they understand by generalized association rule. This is just an implications with X and Y being actually from, so you will have the not only the item from the initial database, but also from the taxonomy. For the setting, so we just take as the item those that we have from the database, and then we are going to add also those from the taxonomy, and including to define the relations, the incidence relations, we need the transitive closure of the taxonomy. And the object will be the set of transactions. So if you to define the incident relations, you take a transactions, and then you want to connect it to an item, then you look if this item appear in these transactions. But if you take a general item, then you can say, okay, a transaction will support a general item if at least one object, if at least one item of this general item will appear in these transactions. So that will be the natural way to do that. And this is also what they have done in their paper. So, but what we have here is that they increase the number of attributes. And if you increase the number of attributes, then we also expect the number of concepts to increase. You can see it, for example, here, the first part from shirts to shoes, this will be the initial database that we have. And from outerwear to footwear, this will be the general, from the general item that we have. So if you look at the line diagrams, then it's clear that from the initial database, we have less cluster than in the second one. Then now the question becomes, shall we keep also the initial attributes in our database or not? If the goal is to reduce the number of attributes, then we should say that it's better to not keep this in the. So if the goal is to reduce the number of attributes, then we prefer here to just use the general attributes without using the initial attribute before. So then in our case, what we call a general attribute, this is nothing else as a subset of attributes that we have before that we put together. Intuitively, there are many possibilities to assign an object to the new attribute that we just created. So if we take, for example, the case of the database that we had before, then it's maybe easier to say, okay, if you generalize, then an object will satisfy the generalized attribute if it satisfies at least one of these generalized attributes. But there's also some other cases. For example, if you look at the, I don't know, the exam or thing, then it's also possible to require that the object will satisfy the generalized attributes if it satisfies, for example, all the attributes that you have in this setting. So how many time can I take? How more minutes can I take? Can you hear me?
Yes, yeah. I believe that's 7 minutes.
Okay.
So, otherwise, we can start a bit later in.
No, it's okay. I will just try to sell the idea of the generalizing attribute, and I will not show all the details. So for what I was trying to say is that once you want to make the generalization, then you put a set of attributes together, and then you can say that an object will satisfy these attributes if at least if the object satisfies at least one of the attributes that belong to this class. This is one way to do that, as this has been done by the example before. Or the second one is to say that the object will satisfy a generalized attribute if it satisfies all the attributes there. This is the example where you have an exam with many components, and then the student has to pass all the part of the exam. It's also possible that you have, let's say, a large module which is having many parts, but then what you require is just that the student should pass at least maybe 60% or 80% of the course forming the module. So then you have this possibility. And it's also possible to not just grouping the attributes, it's also possible to group the object. And this has been done by Susan Prediger. And then when you have the object, the attributes, you can also think about, okay, why just concentrating on object? Why just concentrating on attributes? Or maybe can we combine both together? Yes, there are different scenarios to combine this together. So the idea here is just that, okay, you have a group of objects and a group of attributes. And the question is, when should I relate these two groups? So the easiest way we say, okay, if it's possible to have a connection between one object and one attribute, then you believe that there is a connection between the two groups. This is one way to do that. Or you are more strict and say, okay, these two groups are connected if each object, let's say if all the objects in the group are connected to all the attributes in the group. And you can play with the quantificator by taking all exist and so on. You can play. Or the other possibility is to say that you just look at the proportions. Just say, for example, a certain proportion of the object in the group R should have at least a certain proportion of the attribute in the group B. So then there are many possibilities. Or you can look at the density of the group. So if you look at this part of the context where you have the object and this object is attribute, then you try to look at the density as say, okay, you want the density to be at least a certain, maybe 10%. So that's some possibility to do this kind of generalizations. What we have seen so far is that sometimes, even after doing these generalizations, it's not possible to say for 100% that the number of concepts that you extract from the context are not going to increase. And this is what is discussed in the rest of the slide that I have here. Let us just go to the skip this and then I show you the let's say a bit the idea from the that we discussed here. So we have seen that if we use a Shapley value, we can assess the importance of attributes when we classify some object, and or if when we look at the concept stability. But what we have done so far are to use the algorithm that exists, and we still have to check if we can do some improvement. There are some demos that are available. Then you can look at it for the thing that we have computed here. And we think that if you use the attribute importance, it's possible maybe to also apply it in attribute reductions. And we were planning to discuss the similarity for to reduce the number of attributes. There are some kind of study about interpretability or explaining. So one thing that is in this paper of Cynthia is that we should actually stop explaining black box model if this can harm somebody. For example, you got from the Miguel using compass for judicial decision, or maybe to give the credit to somebody. And why? Because in most cases, explaining the black box model is not really the right thing that we should be doing. So what we should try to do is have to, from the beginning, have already an interpretable model. And in our case, for the concept classification with JSM and so on, these are not black box model because we have the rule in the form of intent imply attributes, and the intent is just already a conjunction of the attributes, and this is somehow explainable. Then the second thing that I want to mention here, we believe that if the model is explainable or interpretable, then this should increase the trust in accepting this model. But then there is a study from the psychology saying that actually it seems to be not the case. So then when people understand the rule, probably they are not, and usually if the rules are quite simple, then they don't trust it anymore. So thank you for your attention, and yes, I will stop here.
Leonard, thank you very much for this interesting talk. I guess that many of us can have questions, and actually I have some of them, but unfortunately we are very limited in time. So if you don't mind, we should switch to the next session, and I would like to thank you for this very interesting talk, and probably I will have some questions by email.
Thank you very much.
Thank you.
Yeah, I'm sorry for the, also not be able to sketch to the timetable.
Thank you very much, both Leonard and Alexei, for managing the talk and the session. Unfortunately, we really have to go to the parallel session, track B, if the ones would like to listen to process mining, and those who would like to stay with data analysis track, they should keep this track, and Alexei will be there as well, I guess. Thank you.